Rebecca, presenting predictive machine learning modeling of urban traffic air pollution, a case study of Entebbe, Kampala Road in Uganda. This is my master's thesis. I've been assisted by my two supervisors, Dr. Osano and Dr. Matara from the University of Nairobi and Multimedia University of Kenya. In my presentation, I'm going to start with a brief introduction, followed by the problem and theories involved, and the methods used, and my findings, and finally with my conclusion and recommendation. Air pollution from the urban traffic is a pressing environmental and public health challenge globally. Due to the rapid urbanization and increasing private vehicle ownership, has led to increased congestion, which degrades air quality in major cities. In these cities like Uganda, there is limited advancement in emission control technologies and integrated transport planning. Many cities exceed the World Health Air Quality guidelines, mainly concentrating on the traffic corridors as the critical zones. In this study, I focused on the Entebbe Kampala Road corridor due to its high traffic congestion, mixed vehicle fleets that create roadside emission hotspots. And this study mainly examined how traffic activity and meteorological conditions jointly shape urban roadside air quality. Urban motorization in Uganda is growing fast, with limited emission control technologies being put up. There is limited empirical research on traffic-related air pollution, and only a few studies apply advanced modeling techniques to quantify and predict emission patterns. This scarcity in detailed modeling has reduced Uganda's ability to link traffic characteristics directly to urban air quality trends. This affects effective emission management and health risk mitigation in fast-growing urban cities. This study addresses this gap by applying interpretable machine learning and statistical models to hotspot corridors. It examined how traffic flow, composition, and weather influence pollutants that I focused on, specifically particulate matter 2.5, photovolatile organic compounds, and carbon dioxide. The major theories considered include traffic pollution theory, which is increase in traffic leads to an increase in pollution, fleet and fuel theory that is mainly emissions depend on vehicle age, fuel type, and maintenance. Emission theory, whereby emissions are more concentrated on areas close to these roads, and the global and local theory, which is mainly globally there are many advanced vehicle technologies and regulatory standards, whereas countries like Uganda still rely on aging fleets, which have limited local modeling capacity, hence creating a gap between the global knowledge and predictive tools needed for effective policy intervention. My methodology, I used quantitative field observation where I carried out traffic counts on a section along Entebbe Kampala Road. This road joins the capital city Kampala to the Entebbe International Airport. I mainly considered a 5-kilometer stretch that was the Namasewa Seguku Road. I did the manual classification counts and also monitored air quality using the airport mobile sensors. Analysis involved descriptive statistics, Pearson's correlation, ordinary least square regression, and for modeling, predictive modeling, I did extreme gradient boost machine learning models, and I used SHARP to interpret the variable influence in prediction models. From my results, it was found that Namasura, which was the starting point of the section that I considered, had the highest traffic, totaling to an average daily traffic of 59,000 vehicles, with the endpoint at Lubowa having a total ADT of 12,909 vehicles per day. The traffic composition was dominated by motorcycles, with saloon cars and light vehicles remaining consistently significant, and heavy trucks had minimal access on all these sites. From the air quality perspective, PM2.5 had a more severe burden during the night time, with a maximum of 863.45 micrograms per meter cubed, and TVOC increased gradually from morning hours until it increased at night to a 1.44 parts per million, and carbon dioxide also reached a highest level at night due to the low wind speeds, which affects the pollutant concentrations in the atmosphere. Pollution risk increases when atmospheric mixing is weak and emissions remain trapped near the road. Night and late periods were the most crucial exposure windows along the study corridor. In my correlation analysis, ADT was strongly correlated with all pollutants, having a 0.9 and above correlation with all the three pollutants, which made traffic density the strongest common driver of pollution. From my regression analysis, as you can see, regression analysis of the pollutants with in relation to wind speed. When wind speed versus TVOC showed that the R squared value was given 0.38, which showed a significant but not very dominant effect of wind on the TVOC concentrations in the atmosphere. In the second graph, where the analysis between wind speed and carbon dioxide shows an R squared value of 71%, which showed that wind speed is responsible for 71% concentration of carbon dioxide in the atmosphere. And for the regression analysis between wind speed and PM2.5, it gave an R squared value of 0.449, which has a slightly significant influence on the particulate matter concentration in the atmosphere. For ADT versus all the pollutants, the R squared value was ranging from 89 to 98, which showed that ADT was a major contributor to this pollutant concentration in the atmosphere, hence showing that pollution is mainly from the traffic volume and the mixes, greatly influenced by wind speed and acceleration. From my SHARP analysis of the different models, PM2.5 was seen as having ADT as its major contributor, followed by wind speed and the small buses, giving the major three largest contribution to PM2.5. TVOC SHARP analysis showed ADT was the highest contributor, followed by wind speed and wind acceleration. In SHARP analysis for carbon dioxide, wind speed and wind acceleration were the major contributors, followed by ADT. and small buses. Machine learning interpretation showed ADT was the strongest driver of PM2.5 and TiVo. Carbon dioxide showed that wind speed, acceleration, and heavy vehicles had the strongest influence. Motorcycles and small buses contributed more to TiVo. High vehicles contributed more strongly to carbon dioxide due to the fuel consumption. Pollution control should therefore target the right vehicle groups and not all vehicles equally. My conclusions from this study are mainly traffic volume, fleet mix, and wind jointly drive PM2.5, carbon dioxide, and TiVo. Nighttime and peak hour conditions create the highest exposure risks. Policies should therefore target specific vehicle groups and not all vehicles equally. Wind speed and atmospheric conditions contribute strongly to pollutant buildup and redistribution. My recommendations from these conclusions were reduction in congestion and stabilization of speed, which can be done by setting up coordinated signal timing, enforcing speed management and freight scheduling, and also encouraging eco-driving campaigns. Acceleration of cleaner fleet transformation, which can be done through strengthening inspections, maintenance, and emission standards for high-emitting vehicle groups, expanding the e-mobility incentives and charging systems for public and commercial fleets across the country, and reducing of subsidies that are imposed on these e-mobility vehicles and motorcycles. Also, use monitoring, enforcement, and public reporting to make regulations visible and effective. This can be done by enabling the roadside pollution management to be used for the public to have access to all that information, dashboards, and community channels. This can increase on the accountability and public engagement, which will increase on the policy legitimacy and effectiveness. Encourage time-sensitive and weather-aware air quality management. And also, from my study, these corridors it showed the significance of the corridor reflecting a wider challenge in rapidly urbanizing cities. This study provided locally calibrated models to support urban air quality planning and policy. It provided evidence for targeted traffic management and emission control policies. And it shows that urban mobility is a climate, air quality, and public health issue. The way forward from this would be to encourage expansion of monitoring of air quality across different seasons and corridors, use of more interpretable and advanced models together for better urban decision making, integration of transport and urban planning, and treating of cleaner mobility as a core strategy for resilient and low emission and livable cities. My references: World Health Organization and Matara 2024, Outbury 2023, GAL 2022, and Musa and Olibosoya 2020. Thank you.